We now start our discussion on sequential circuits. Let me try to explain what we are going to talk about in the next few lectures. So far, the kind of logic circuits, the design, the optimization that we had talked about, they were basically concerned with combinational circuits. If you recall, in a combinational circuit, the outputs depend only on the inputs that you apply at that particular point in time. In contrast, when you talk about a sequential circuit, there the output also depends on some kind of previous history, what kind of inputs were applied earlier. We shall be talking about examples later. So, for this kind of a sequential circuit, we need to store or memorize some information. Okay? So, the topic of our discussion in this lecture is latches and flip flops, the first part of it. These latches and flip flops essentially constitute the basic building block using which we can store some information. Well, information in this case we are talking about bits, we want to store the zeros and ones. Okay? So, let us see. So, as I have just now mentioned that for a sequential circuit, the outputs of the circuit will depend not only on the inputs that we have applied, but also on some kind of past history of the system, which in other words means that the system has to memorize which state it is in. Let me take a very simple example to illustrate what we are trying to talk about. Well, you imagine that you have built a system, an automated system, whereby whenever someone enters a room, the light turns on automatically. Well, it is not a very big thing. You can have a sensor which will give a pulse, a 1, whenever there is an interruption in some light when a person enters, and there will be a circuit which will be turning on the switch of the lamp whenever that kind of signal comes. Now, what you want is whenever that person comes out of the room, the lamp should automatically be turned off. So, there can be multiple persons in the room, right. So, the system should remember or memorize how many persons have entered the room so far. Suppose there are 10 persons who have entered. So, unless and until all the 10 persons come out of the room, exit the room, the lamp will not be switched off. So, for a circuit like this, the circuit or the system has to remember how many persons are currently in the room, and that constitutes the state of the system. This is the basic idea behind the design of sequential circuits. Well, there are two types of sequential circuits we can talk about later, synchronous and asynchronous. Okay. Mostly we shall be discussing about synchronous sequential circuits. Okay. So, in order that the circuit can memorize the states, we have to have some kind of basic memory elements called latches and flip flops. So, these latches and flip flops will be our basic memory elements using which we can store the state of the system. And these latches and flip flops, there are various types, we shall be discussing the various types and how they are designed in the subsequent discussions. Now, what we are trying to say is how to design a circuit in which we can store some information, store the value of a bit, whether it is 0 or 1. So, storing a bit is the most basic form of information storage. Whenever we have multiple bits, we can store a word. Okay. So, let us see what is the basic requirement for storing a bit electronically. What do we mean by storing? Where do we store? Okay. You see, when you talk about some device like a magnetic disc, there we have an idea, well, magnetically we are trying to store something, we are trying to create tiny magnets on the surface of the disc. Which side is the north pole, which side is the south pole, that will determine whether you are storing a 0 or a 1. But in an electronic circuit, how do you store? Let us try to understand that. Well, here what we are saying is that if we have a cascade of two NOT gates, NOT gate means inverters, with feedback, that will constitute the most basic form of storage system. This will constitute a stable state of the system. What do you mean by that? Let us try to see. Suppose we have an inverter like this, there is another inverter like this, two NOT gates, they are connected in cascade with feedback. Now, in such a circuit, let us say, suppose, assume that somehow this input is at logic 0. Well, if this input is at logic 0, the output of the NOT gate will be at logic 1, output of this NOT gate will again be at logic 0, and that same 0 is being fed back here. You see, this is a stable state of the system. Whenever we set this system in this state, the values of those zeros and ones will never change. It will memorize this state as long as power is on, the circuit is powered on, it will remember this state. Let us say if we take the output from this point, let us say from this point if we take the output, this point is at state 0. Now, somehow if you are able to change it, suppose if you are able to make this 1, which will make this 0, which will again make this 1, and the same 1 is fed back here, then we say that the output is 1. So, this configuration, a pair of NOT gates or inverters connected in a chain like this, this is the basic memory element and constitutes a stable state. And as you can understand, whenever a circuit is in this kind of a value, this 1 will remain a 1, because no other circuit is trying to make it 0, because this NOT gate output is also 1, the same 1 is again applied as an input here. So, it constitutes a stable system. Okay. This is never deleted or modified unless we change something externally, right. Okay. But in practice we need something more. You see, what we saw that we have a stable system that can be designed using two cross coupled NOT gates, but what we have not talked about so far is how to set the output values to 0 and 1 depending upon our wish, depending upon our requirement. So, we also need to have that kind of a circuit that from outside we can set the circuit state to either 0 or to a 1 as per whatever we need. Okay. So, for that reason, for that purpose, we need some additional circuitry, and depending on what kind of additional circuitry you are using and what is the exact functionality of your circuit, we can distinguish between various kinds of latches and flip flops accordingly, and this we shall be discussing in our subsequent slides. Let us look into this cross coupled inverter once more in a little more detail. So, in the diagram on top we are showing these two NOT gates which are connected in a chain like this. The input is V in 1, the output of this gate is V out 1, which is applied as the input to the next gate which you are calling V in 2, and the output of this gate V out 2 is again fed back here and is applied as V in 1. Now, you see one thing, whenever we have a single inverter like this, a single NOT gate. So, if we try to plot the input versus output voltage, this is the input voltage and this is the output voltage, let us say O. The curve typically shows a behavior like this. So, when the input, this is 0 volts and this is some maximum. So, when the input is 0, the output is at a high level, and there is a point where the output slowly starts to change, and beyond a point the output is more or less at low level. Okay. This is how inverter works. Now, let us see this diagram. In this diagram, we have plotted V out 1 on this side and V in 1 on this side. This is the first inverter, and the solid black line shows the characteristic curve just like I showed for this first inverter. Now, for this second inverter, this V in and V out are reversed, right. This V out of the first gate will be V in of the next gate, and V out of the next gate will be V in of the first gate. So, to show the characteristic curve of the second gate, we just reverse the axis. So, along the y axis we show the input V in 2, and along the x axis we show the output V out 2, and we have a similar curve like this. This is the blue curve shown like this. Now, we are showing both the plots on the same curve, because the output of one gate is actually the input of the other gate. Okay. Fine. So, what we say here is that there are two regions of the system, one out here and one out here, where the system is stable. Stable means whatever is applied in V in 1, that is regarded as logic 0, and the output will be logic high, and this V out 2 will also be logic 0. So, V out 1 will be at logic high, V in is 0, V out is high. So, there are two regions. If it is V in is high, it will be low, output will be low. If V in is low, the output will be high. But in the middle region, it is not a very stable thing, because if the input changes, the output changes very sharply. If you look at this curve, in the middle part the slope is very high. So, if the input changes a little bit, the output changes pretty sharply. That is considered as a metastable or an unstable state. So, if the circuit is in a metastable or unstable state, it will try to move into one of the stable states as quickly as it can. Okay. So, in terms of a pictorial representation, if this is my input voltage range, so on the two sides we have two stable states, and whatever is in between, this is unstable or metastable states. So, it is like a ball. If it is in the metastable state, it will always try to roll into one of the stable states, right. Okay. Let us move on. Now, let us come to what we are actually trying to discuss here. So, how to design the storage elements. So, we first talk about the design of storage elements called latches. A latch is nothing but a storage element or a storage device that can store a single bit of information. Okay. It can store either a 0 or a 1, which means it has two stable states, 0 or 1. Because there are two states, two stable states, and it can switch from one to the other, it is sometimes also called a bistable device, and since it switches between two states, it is also called bistable multi vibrator. It vibrates between two states, something like that. So, this is also a name which is given, bistable multi vibrator. And latches are level sensitive, means suppose I am applying some input. So, when I am applying input, let us say I have applied a 0 or a 1. So, when I am applying a 0, I am applying a continuous 0. When I am applying a 1, I am applying a continuous 1. So, the circuit will react to the voltage level. That means, how long I am applying a 0, how long I am applying a 1. It will not look at exactly when I am changing it from 0 to 1 or so. Level sensitive means this circuit operation will depend only on the voltage levels, level of the voltage that I am applying in the inputs. Okay. All right. So, the different kind of latches and also flip flops that we shall be talking about are set reset or SR type, delay D type, JK. Okay, this is also the short form for Jack and King, but it is not very commonly referred to. So, we simply call it JK, and T means toggle. These are the 4 most widely used flip flops and latches. We shall be discussing them. We start with the most basic kind of a latch, this set reset latch or an SR latch. This is the most fundamental of the storage element, and let us try to understand how this works. Well, a set reset or a SR latch consists of a pair of cross coupled NOR or NAND gates. Now, in this diagram I am showing cross coupled NOR gates. So, why I call it cross coupled? Because you see there are 2 NOR gates, the output of one is fed to the input of the other. Now, let me talk about one thing. I mentioned earlier that 2 inverters connected in cascade with a feedback constitute a stable storage element. Now, suppose these inverters I modify into a 2 input gate. Let us say I make this a NOR gate, I make this also a NOR gate, and I apply another input here and I apply another input here. So, one of them I call it S, another one I call it R. Now, the purpose of R and S are to forcibly set these lines to 0 or 1, whatever you want from outside, which for a simple NOT gate chain it was not possible to do, because there was no external input. So, SR flip flop is just an extension, this latch is just an extension of that inverter pair feedback with feedback, that kind of a chain, but we have replaced the inverter by a 2 input gate, in this case NOT gate. So, you see these 2 circuits are actually identical. So, here we have drawn it in a slightly different way. The NOT gate with the R input, this is the one, the output of which is going to the input of the other NOT gate, output of which is going to the input of the other NOT gate, and the other input is coming S. So, you see other input is coming S, the output of this coming to the input, output of this is again coming to the input here, R is applied. Okay. So, these 2 circuits are same. Okay. Now, let us try to look at the functional behavior. So, how does a SR flip flop behave? Well, this I shall be explaining in more detail later, but let us look at it just at face value, whatever I am saying here. Suppose I apply S equal to 0, R equal to 0, which means in this circuit S is 0 and R is both are 0 and 0. So, the output Q and Q bar, one is the complement of the other. Okay? Q and Q bar are the complement, Q and output and its complement. So, it will be storing some value. Suppose Q is storing 0 and Q bar is the complement of that. So, if we apply R is 0 0, you see this 0 is coming here, 0 and 0, this output will be 1, okay? And 1 and 0, output of the NOR gate will be 0. So, there is no change. Similarly, if you see if this is 1 and this is 0, then also no change. This 1 will remain 1 because 0 0 is 1 and 1 0 is 0. Therefore, if we apply 0 0, there is no change in the outputs, right. This is the first one. Now, suppose I apply 0 1, S equal to 0 and R equal to 1. Now, for a NOR gate, if we apply a 1 to one of the inputs, the output is forced to become 0, right, and this 0 and 0, this will become 1. So, you see for this case Q is 0, Q bar is 1. So, whenever I have to set the output Q to 0, I will have to apply S equal to 0 and R equal to 1. Similarly, if I apply the reverse S equal to 1 and R equal to 0, then this 1 is the input of this NOR, this gate will become 0 and 0 0 this will become 1. So, the output is 1. So, whenever I want to make the output 1, I have to apply 1 0. Now, the last row I shall be explaining a little later. It says that if I apply 1 1, this will be an invalid combination. Well, I shall be explaining this a little later. You see, means our basic purpose is fulfilled. We have been able to set the output to 0, we have been able to set the output to 1, or if we do not want to change, we also have an input using which you can keep it in the same state as it was. So, we have designed a very basic storage element which can store either a 0 or a 1, or it can also remember whatever it was. If I apply 0 0 in S and R, there will be no change in the outputs. Okay? Fine. Now, this is the circuit diagram using NOR gates. Now, just using NAND gates also you can design a very similar circuit. The only change with respect to this table, well just one thing let me tell you also, I did not mention. For a combinational circuit, when we talked about the input output behavior in the form of a table, we called it a truth table. But for a sequential circuit, such an input behavior we refer to as a state table, because it also captures the state of the system, not only the input output behavior. Okay? So, this table that we are showing here, this actually is a state table. Right. Well, here for the NAND one, the only difference is we are applying S bar here and we are applying R bar here, the NOT of S and R. Now, you can verify the operation. Suppose S is 0, R is 0, the first row, which means S bar is 1 and R bar is 1. For a NAND gate, let us say the output was 0, this was 1. So, 0 and 1 for a NAND gate, output will remain as 1, and 1 and 1 output will remain as 0. So, same state, no change. Similarly, for 1 and 0. So, if I apply S 0 R 0, there will be no change, right. So, if I apply S equal to 0 R equal to 1, S equal to 0 means S bar is 1, R equal to 1 means R bar is 0. NAND gate, any input 0 will force the output to be 1, 1 and 1 this will be 0. So, you see the output is 0. Similarly, if you reply just if you apply the reverse S equal to 1 R equal to 0, S equal to 1 R equal to 0. So, this 0 will make it 1, this 1 will make it 0. So, the output is 1, right. So, now let us see that why the fourth combination is considered to be invalid. Okay. So, let us try to just explain this with respect to this NAND level diagram. Now, what we have seen so far is for S equal to 0 and R equal to 0 combination, the behavior of the circuit is there is no change, right. And we are saying that S equal to 1 and R equal to 1, this is an invalid combination, we should not apply, right. Now, let us see that what will happen if I apply S equal to 1 R equal to 1 here. Let us see, S equal to 1 means S bar is 0, R equal to 1 means R bar is 0. So, because both the gate inputs are 0, so both the outputs will be forced to become 1. Well, so you may argue, one way of arguing is, well, I am calling them Q and Q bar. Now, because both of them are 1 and 1, so it is wrong, that is why this is invalid. Well, but I can argue in a different way. Suppose I have designed this circuit in such a way that only Q is available to you, Q bar is not available. Then I can say that if I apply S equal to 1 R equal to 1, Q will always be 1 as the circuit shows. So, there is no ambiguity here. So, where is that ambiguity coming in, or why we are calling it invalid? Well, we are calling it invalid because you see this S equal to 0 R equal to 0 combination is supposed to be a combination which will not cause any change. So, what is the meaning of S equal to 0 R equal to 0, which means I have applied a 1 here and I have applied a 1 here. So, my circuit state was this 1 1 it was. Now, if I apply 1 1, you see this 1 and 1, this will become 0, this 1 and 1, this will also become 0. Now, if both these two gates are exactly of the same speed, then this 1 will be changing to 0 at the same time. Then again 0 and 1 will be 1, 0 and 1 will be 1, they will again change back to 1 at the same time. But in reality what happens, two gates are never of the exactly same speed, one will be slightly slower than the other because of fabrication differences and differences in characteristics. Suppose this gate is faster and this gate is slower. So, what if this gate is faster, then this 1 1 was there, let us say 1 1 was there earlier, this 1 and 1 will cause this to become 0 first and this 0 will now be fed back to make it 1. So, now we have a stable state 0 and 1, but if this gate was faster, then the reverse would have happened, we will get 0 here and 1 here. So, the confusion is after applying S 1 R 1, if we apply S 0 R 0, you cannot definitely say whether the output will become 0 or 1, it will depend on the relative speeds of the two gates. This is a phenomena which is called race condition. Okay. So, this is exactly what I explained. Race condition is a scenario where the final result depends on the relative speeds of the gates. So, I said if I apply S R 1 and then apply S R 0, so you cannot definitely predict what the output will be. It can be either 0 q bar 1 or q 1 q bar 0 depending on the speeds. Now, just one thing, if we want to extend the design of an SR latch to a gated latch, you see here we have made a very small change, we had added an enable input. We had added a third input and we have added two NAND gates here, and this NAND implementation was already there, the basic SR latch S bar R bar, we have just added this and we call this as S, we call this as R. We say when E equal to 1, the latch is active, when E equal to 0, the latch is not active. So, now this state table will look like this, when E equal to 0, then irrespective of what you are applying in S and R, there will be no change, NC means no change. Next 4 rows indicate when the latch is active, E is 1, when S is 0, R is 0 just like previous, ends no change, 0 1 will cause the output to become 0, 1 0 will cause output to be 1 and 1 1 is an invalid combination. Now, let us work out one combination, let us say enable is 1, let us say 1 0, the 4th row 1 0, S is 1, R is 0. This is a NAND gate, 1 and 1 will make it 0, 1 0 will make it 1, this 0 will make this output 1, 1 and 1 this gate will make the output 0. So, the output Q will be 1, 1, right. So, this circuit works perfectly well, okay. And just by using an enable input you can either activate it or deactivate it by setting E to 0 or 1. You can have an alternate design, instead of that NAND latch you can have the NOR latch, only difference is instead of NOR gate you need to have AND gates, in place of NAND gates which you had earlier, here you will have only AND gates. So, I leave it an exercise for you to verify that this circuit also works as an SR flip flop and this same state table is satisfied here. Okay. These are just two alternate designs. Okay. Now, come to another kind of a latch which is much simpler type, which is called a D latch. Now, what is a D latch? Just as compared to an SR latch which had two inputs S and R, a D latch has a single input called D. And basically, when you enable the latch, the value you are applying at D will get stored inside the latch, very simple. This is how you can design a D latch. You see, the second design is easier. The first part which you see here is just an SR latch, where this is your S input and this is your R input. You take an inverter, D you directly connect to S and D bar you directly connect to R, you get a D latch. Well, if you start with a NAND based design, then your design can be like this. You can save one inverter here, means the one gate less is required, D enable, and the output of this, when enable is 1, D will become D bar, this D bar can be fed here and you can directly connect here. So, these are two alternate designs of a D flip flop, D latch. And for D latch, how it behaves? If the enable is 0, irrespective of D, there is no change in the output. If you are enabling the latch, if D is 0, output will become 0. If D is 1, output will become 1. Whatever is the input, that same value will get stored in the output. Okay. This is how a gated D latch works. Just as I mentioned in the diagram, that if you have an SR latch available with you, you can construct a D latch just by using a NOT gate. D you apply directly to S, and with a NOT you can apply it to R. So, of course, we shall see later that how any arbitrary kind of flip flop or latch can be converted to other type of flip flop. But in this lecture, we stop here, and in our next lecture we shall be looking at the other kind of designs of latches and flip flops, what are their characteristics and how they can be converted from one form to the other. Thank you.